Hello, my name is Sai Sri Dudala, and I'll be running through the MATLAB code that my mates Jonathan Henry and Max Wong have created. So we chose the linear systems problem because it was the most pertinent to chemical, electrical, and mechanical engineers, and they will be also using problems and code like this during their sophomore and upper level classes. So for the first problem, the purpose of the program was to turn a user input matrix into the upper triangle form and to find the corresponding x values of the system. The program asks the user to input a matrix and it will store that as MO. The output variables are TT matrix and output, which are top triangle form of the matrix, and the output values for each x value respectively. There are also some other values that help control the code, which is the decision whether or not to continue inputting more matrices, the variables to measure the size of the matrix, and the menu for asking the user if they want to run the whole code again. What this code will first do is it will ask the user to input a matrix and then call the function upTry, which will change the user input into an upper triangle form. This code takes the function, which is an n by n plus 1 matrix, and turns it into the upper triangle form. It takes the size of the input matrix, creates a matrix of ones of the same size as the original input, and then it will, as a result, turn it into the upper triangle form. The program will then check and notify the user if they have entered a system that has more than one solution. And if it does have more than one solution, it will ask the user to enter a new matrix. The program will then output the upper triangle matrix and call the function named backsub, which will take the output from upTry using back substitution to calculate the values x1 through xn. This function finds all the x values through back substitution, and it solves for each x value column by column and then multiplies the solved x value to every row in the same column. And then it subtracts those values from the overall value in each row, and then the function moves on to the next column and so on. At the end, the program will output the formatted fprintf statement, and if there are many solutions, it will display an error saying there are infinitely many solutions. It will also ask the user if they would like to enter another linear system. If the user selects yes, the whole code will run again. If the user selects no, it will then move on to problem 2. Problem 2 asked for the implementation of a user-defined function called bisectRoot. This function would be able to take the input vector and change it into A1, A2, A3, and A4 vectors, where A corresponds to the coefficient of that order. It then uses the bisection method to calculate the maximum possible error after every iteration. The program asks the user to input a vector, two upper and lower bounds for the guessing roots, and the user input tolerance for the result, and it would output the maximum error, the approximate root, the number of iterations, and the maximum possible error, and two figures that are visual representations of the data. There are also controlling variables for this problem that asks the user if they would like to run the problem again, and also data validation. At first, the program will ask the user to input a vector, and it will call the function bisect root, which will take the input vector and change it into A1, A2, A3, and A4 by the bisection method, and then it would also plot the function. The program then checks that the bounds that the user have inputted are either both positive or negative. If not, the program will ask the user to enter either one positive and one negative. It will also ask the user to input two new bounds if there was an error detected in the entering of the variable. The program will then calculate the approximation root, the maximum error, and the number of iterations, and output those variables in a formatted fprintf statement. It then creates a plot of maximum error as a function of iteration and calls the function bisect root2, and then which then plots the difference between each iteration's approximation of the root and the final approximation of the root. It will ask the user if they would like to try again with a different set of inputs, and if the user selects no, it will ask the user if they would like to run both programs again, and if the user selects yes, it will run through only this portion of the code. This menu statement runs through the whole code or ends the code right there. For problem 1, some assumptions we had was that the user can enter any matrix only if the matrix has dimension nx, n by n plus 1. We use the same test cases from the prompt and also the test case for backs up the function. And for problem 2, we assume that the user can enter any bounds only if they are not both positive or negative. We also use the root approximation and all other information for the test cases from the given prompt. I will now run the code for each test case. And for the first part, we'll use the test cases given by the prompt, which will return these values for TT matrix and the x1, 2, and 3. The code will also ask the user if they'd like to enter another linear system. It will choose yes and enter a second one. We didn't enter it properly, so it asks us to re-enter enter the proper matrix size and output the respective variables. And then if you select no, the program will then move on to problem 2, which will ask us to input a vector, the upper and lower bounds with the two guessing roots, and the tolerance for the answer, which will output these two figures, which is the difference between each iteration and the approximation of the root, and the maximum possible error versus each iteration. It will also output the root approximation value, the max E, and the number of iterations. It will also ask us if we would like to try again, and we will do so with a different set of matrices. We will use the same upper and lower bounds for the two roots, and we will also use the same tolerance, and we will get the same output, two graphs, the difference between each iteration, approximation of the root, and the maximum possible error versus each iteration, and then different number outputs for these. It will also ask us if we'd like to try again, and if we select no, the program will ask the user if they would like to run both programs again. So if we select yes, it will come back to the first prompt. This code could be used by an engineering student in their upper level classes to solve some of those harder problems that they encounter, and also by professional engineers in the field to solve some of the problems they have in their work much more easily and faster, increasing their work rate and workflow. Limitations of this code are that it can only be applicable to linear systems, and it only turns a matrix into the upper triangle form. So this code will only work for one type of problem. That will conclude the walkthrough of the program. I hope you have learned a lot about a program, how it works, how it operates. One key thing I would like to state is that user-defined functions really clean up the code and make it much more organized. And it's not just one large block of code, it's broken up into different functions which the user can look at and then know what each function is doing. This code is very organized. Each line is commentated and explained thoroughly, and each part of the code is explained in what it does and what it achieves. But that will conclude the walkthrough. I hope you have learned a lot. Thanks for watching.